Hi, I'm Jed Kimbrough, and this is my final project for EE321 at OIT's Portland Metro campus. Here I have my power supply. On the back side I have a power switch, plug, and a fuse here. Let's see if I can get some better light for you. On the front side, we have our control and a digital output. Inside the box we have the circuit. You can see the bridge rectifier here, 1, 2, 3, 4 diodes. My Zener diode to provide the constant voltage to the input of our op amp. This large ceramic resistor here biases the Zener. We have a BJT, this is a TIP 120, to provide the constant current out. It's provided, its source is the op amp here. What else? We've got the feedback resistor, or transistor, excuse me, here. This one is a 222A to draw current off the op amp if it gets too high. That one's biased by a large ceramic capacitor on the bottom. Well, physically large, it's a 1.5 ohm. Also on the bottom side of the board you can't see is a 4700 microfarad capacitor for the peak detector for the rectified voltage. Here we have our voltage divider to control the gain on the op amp. This is the LM741. One of these here is our 10 ohm or 10 kilo ohm resistor to ground, and one of these is a 500 ohm in series with our 10K pot. I used the 500 ohms to kind of adjust the base output for the op amp to close to 5 volts. Additionally on the circuit here we have the 7-segment display that I wired up. That's these 3 wires here. That's provided the integrated circuit. It's provided power off of the rail right after the peak detector. So I've tied in here this YOLO wire brings the ground rail over to the same side as the positive rail. These 2 wires are tied in, and then here is the probe for that IC. The output for our circuit, also here, the same node as the probe for the IC, is brought over with this jumper wire here for the positive side, and the negative rail on the underside of the proto board ties in down here. Alright, let's hook it up to power and see what it can do. Okay, so I've hooked it up to the wall and tied into the output with these micro clips here, and those go to my voltmeter. I've hooked it up so you can see the range here. 10.1 volts, 5.24 here, 5.22. These things are not great, but they're close enough. What I'm going to do is I'm going to use this display to read out voltage, and I'm going to switch my multimeter over to read the current on the load. Since I'm doing this at home, I don't have access to an oscilloscope at the moment. Okay, so I'm starting off with a 1.5K ohm resistor on the load. I've got that here. Oh, and what you can see, it's a little tricky to do this with just one set of these micro clips. Just wrap the leg of the resistor here around my probe. And as expected, 5.24 volts divided by 1.5K at 3.5 milliamps. I think you can see that. I'll turn it up. Still have our 10 volts, 6.9 milliamps, and we're good. I'm going to switch this out for a smaller resistor. Okay, I could not find a 20 ohm resistor, so the next best thing, here's a 30 ohm, and unfortunately, as you can see, my voltage has started to drop. I am down to 9.83 volts, and looks like I'm limited at around 313 milliamps. This is not the same way the circuit was reacting on the breadboard. Before I decided to solder this thing up, I was getting right around 400 milliamps for my limiting current. Alright, I'm going to switch this out for a 10 ohm resistor. Before I do, let's see what our range is. The lower range is still fine, right where it was before, but the high end is starting to drop off. Alright, I'm not sure how this circuit's going to react with 10 ohms, so you're going to find out with me. We'll hook this up. The low end still fine, 463 milliamps. Nothing seems to be getting too hot. We'll crank this up. We're stuck at 5.6 volts here. $497 milliamps. Alright, for fun, let's go ahead and hook up this little motor I got here. It's going to be hard for you to see it spin, but you can see the torque there, and you can hear that. Alright, there it is. It's my 5 to 10 volt linearly regulated power supply. Thanks for watching.